Okay. So, we start from where we ended last time. Suppose there are two jointly random variables. Okay. This much is x and this is dx, this is y, and this is dy, we have seen this thing, the meaning of this we know, y by x it means when we constrain capital X to lie from here to here, under that condition, under that constraint, what is the probability of capital Y lying from here to here. So, whether here or here or here does not matter, that probability. Now, suppose capital X and Y are such, there is absolutely no relation between them. As I told you, one could be temperature, capital X, maybe another one is say maybe rupee value of dollar. So, absolutely no relation. So, under such cases, if physically y does not depend on x at all, so it does not matter whether I constrain capital X to lie from small x to x plus dx, or maybe x prime to again dx, whether here, okay, because there are no relation between them. So, it does not matter whether temperature is from here to here or here to here. Okay. This will always be same in both the locations as long as dy is fixed. Okay. So, it will be like the chance of capital Y falling from small y to y plus dy. It will be that, it will be independent of capital X, because physically if they are such that there is no relation between them. So, there is no point, there is no meaning of the statement that I am constraining capital X to lie from here to here and then measuring y, and capital Y chances of that falling from small y to y plus dy is this much, but that will be independent of where capital X is. So, this will then turn out to be, this is independent of that. So, it will simply be this, just general as we have seen earlier, just probability of capital Y lying from small y to y plus dy, that was this. The conditioning will have no effect. In that case, P x y, as we have seen earlier, this you could write as free variable this you have seen already, the constraining variable capital X. So, now it will be the probability density of this. So, this is, as you have seen, under the above assumption that there is no dependence of capital Y on x and vice versa. This will be simply P y P x x. There is a product of individual probability densities. Individual probability densities are also called marginal densities, and in this case we say x and y statistically independent. I abbreviate it as SI, statistically independent. Then the joint density is a product of marginal densities, or this conditional density has no effect of the condition. So, if the conditioning variable is capital X, that goes, it becomes just the marginal density of the free variable y. All right. You can generalize it to a case like 3 variables. Suppose now you have got 3 random variables. X, this is y, this is z. X, so this much is dx, y, and this much is dy, and this is z, and this much is dz. In that case also, my drawing is not good, so let me erase this part. This much is dx, this is y, and then sorry, this is dy. Then okay, now I got it. So, here suppose I consider this thing P, z is the free variable suppose at x y as an example only, dz. We have seen all, what does it mean? If I constrain capital X and y to lie, capital X lying from here to here, capital Y lying from here to here, that is this planes, whether here or here or here. Subject to that, the probability of capital Z lying from small z height to height small z plus dz, that was equal to this, proportional to dz and proportionally constant. But suppose capital Z is such a random variable, it has nothing to do with x y, no relation. So, it will not depend on the constraint, it will be simply equal to just P z z dz, marginal density. In that case, we will say, sorry, in that case, we will say Z is SI, statistical independence with x, y, and In this case, we will have P x y z you can write as P z by x y times P density of joint density of x y, and this is nothing but P z only now. All right. So, you can write like this. That means, if they are if out of the all the random variables, some of them are statistically independent of the rest. So, you take the joint density, or in this case marginal density, because you have only one, but you take the joint density of one set here and multiply by the joint density of the other set here. The two sets are statistically independent. If further capital X also and Y also are statistically independent between themselves, then this again further you can break as P capital X of small x into P capital Y of small y. So, the three are statistically independent in that case. So, depending on the case, you can break up like this. All right. This is one thing. Next, now we consider one expression that was considering earlier, covariance between two random variables x and y. Covariance it was denoted by C x y, expected value of minus the mean, y minus the mean. Its physical meaning was explained that time. This is the AC part, incremental part around the mean, this is the incremental part around the mean. If x and y are highly related to each other, either both will go up above their mean together or below their mean together. So, product will be positive in any case, plus into plus plus, minus into minus still plus, and when you average out you get a good number, positive number, or it could be such when it goes out maybe it goes down and vice versa. So, in this case if you average out you will get a negative number of good magnitude, but if there is no relation between them, then sometimes this increment could be positive and then it is positive, and again when this is positive sometimes it could be negative and vice versa. So, when you take all cases and product and average, it may cancel each other and you get close to 0. So, that gave us an idea about the degree of correlation between x and y. If covariance is high, they are highly correlated. High means high magnitude. If covariance is 0, they are not correlated, they are called uncorrelated. All right. So, now this E is actually, there are two random variables. So, now I can put x y, and E is a linear operator. So, if I now break it x into y minus mu x y minus mu y y plus mu x mu y. So, it will be E x y on this, then minus E x y on this, then minus E x y on this, plus E x y on this. So, if you apply E x y on this, so product of the two random variables, they are average expected value. It is called correlation. It is denoted by correlation. And then E x y on this, of which mu x is a constant. E x y means what? Multiplying by the joint density and integrate. So, mu x is a constant, not random, it will go out. So, it will be mu x times E x y of y. But I told you, I in previous lecture have shown that if there is a function and the function here is just y itself, it is a function of one variable and you have got more than that variable here, you have got other variables also with respect to which you will carry out the expectation, then those variables simply drop. So, x will drop. So, this is equivalent to E y y, which is equal to mean of y. that is mu y. Similarly, E x y of 1 minute x mu y, just a minute, it is x into mu x into y, mu y into x, this will be x. So, again mu y will come out, E x y will work on x. X is the function, but it has only one variable x. So, y will drop out, it will be E x x, which is mu x. So, mu x, and then E x y on this. So, this times the joint density integrated. There is the meaning of E x y of something is a constant. E x y, that means this into the joint density P of capital X comma y bracket small x small y dx dy integral. So, this will come out of the integrals because this is constant, and that integral will be 1 because it is a double integral of that joint probability density. So, it will be just mu x mu y. So, minus mu x mu y minus mu x mu y plus mu x mu y. So, it will give rise to r x y minus mu x mu y. This means, if x y are uncorrelated, then C x y 0, which means if it equal to 0, correlation is product of the means. And often we deal with random variables which have 0 mean. So, if mean one of the means is 0 or both the means are 0, then uncorrelated, which means this, that will also mean correlation also 0, covariance 0, correlation also 0, all right. But in general, uncorrelated means covariance 0 and correlation is a product of the means. Only if the means are at least one mean is 0, then correlation also is 0, but not always. This is the meaning of uncorrelated. Now, suppose x, y are statistically independent. That means, this joint density is product of the marginal densities. It was taught in the previous class. In that case, r x y, which is r x y is the expected value of the product. So, double integral small x, sorry, this is capital. So, capital X takes values small x, capital Y takes values small y into the joint density dx dy. There is a general formula. This is a function of two variables, which is the product itself multiplied by the joint density double integral. But the joint density, if you can break like this because they are statistically independent, then we have one integral in which x will occur at this p and dx, another integral but this is the mean expected value of x, this is the expected value of y. So, this is mu x mu y. So, if they are statistically independent, r x y is the correlation is the product of the means they are uncorrelated, the covariance is 0. This means, if x y are statistically independent, then Cxy 0, because Rxy is product of the mean as required here, means xy uncorrelated. So, if they are statistically independent, that is, if their joint density can be broken, can be written as a product of the individual marginal densities, probability densities, then the covariance is 0, correlation is the product of the means, and they are uncorrelated. But the converse is not always true. That is, suppose this is given, that covariance is 0, or equivalently Rxy correlation is product of the means. That does not necessarily mean that the joint density you can write as a product of the individual densities. That happens only once, when capital X and Y are called jointly Gaussian random variables, that I will consider later, but not in general. This always true. If statistically independent, they are uncorrelated. But if they are uncorrelated, it is not guaranteed that they will be statistically independent, that is, the joint density can be written as a product of marginal densities. Okay, that depends on the particular density, and there is a particular probability density form called Gaussian. So, joint Gaussian for two random variables, that we will see later. Okay. Now, with all this background, I consider multiple random variables, not just x or y or xy or xyz. I will have, say, in general maybe p number of or n number of random variables, joint random variables. So, let x1, x2 instead of y, x1, x2 dot dot x maybe p joint real continuous random variables. That is, in every experiment you are observing these separately. One could be temperature, one could be humidity, one could be other things, I mean, all together. There may be some relation between them, may not be. They are observing, all right. So, they have a joint density or all those things. Everybody has a mean. So, Ex1, Exi of xi is a mean of that mu I. So, x1 has been mu 1, x2 has been mu 2 dot dot dot, all right, and I form a vector small x bar underscore I put these variables in a vector form, in a stack. All right. Then from each, and also I put the means in a vector form. Then consider this x minus mu, that is x1 random variable minus mu 1, x2 minus mu 2 dot dot dot. So, increment or the incremental part around the mean, it can be positive, negative, like the AC component. This is the DC, this is the mu is the DC average, and this is the AC around the mean. So, fluctuating, sometimes positive, sometimes negative, same here, same here. Okay. Now, if I consider this thing x minus mu vector as it is, this column vector into its transpose, it will be a matrix, column into row. So, ith row, any ith row and jth column maybe jth column this element will be what? Ith guy, and when it becomes row, jth guy, that is xj minus mu j, their product. If you see the way this matrix is formed, this is a vector, it is row. So, first element into first element of this, first element into second element of this, first element into third element of this, that is how the first row formed. Then second element into first element, second element into second element, second element into third element, dot dot dot, there is a second. So, ith row is formed how? Ith element times first guy, that is here first, ith element times second guy, that is here second, like that. So, ith times the jth. Okay. So, this will be xi minus mu I into xj minus mu j. All right. And if I apply now expected value on this, expected value with respect to all of them, x1, x2, dot 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 up to xp. So, this E will work here, but you see only two random variables xi, xj present. So, as I told you, all others will drop off, only xi and xj will remain. So, it will be E of just xi, xj, all other random variables will go, that I have told already shown earlier. Only those who are present in this function, on them those variables only will occur. So, you will get, and this is nothing but covariance between these two random variables. So, C xi xj. All right. So, this matrix is called covariance matrix. Matrices are shown by me by uppercase letter with an underline. Vectors, column vectors are shown by me by lowercase letter with an underline. But if there is no underline, then it is a scalar. It could be uppercase, lowercase, does not matter. So, I repeat again, capital letter underscore matrix, lowercase letter underscore vector, and if it is not underscore, it can be lowercase, uppercase, but it is your is a scalar. Fine. So, this is the covariance matrix. Now, you see one thing, if I now take the j comma ith row, it was I comma j, by the same way j comma ith, in the same token, you will have this will be E, again only first j comma I, first take this product. So, xj minus mu j, now that will multiply xi minus mu I and only these two random variables will survive here, others will drop off. So, it is this, but these two things are same, xi minus mu I, xi minus mu I. It is first here, it is second here, xj minus mu j coming second, it is coming first, but product is same. So, they are same. So, C is such a matrix, C I comma j is same as C j comma I. So, it is a symmetric matrix. Another one, C I comma I, that is the diagonal, ith row, ith column, that will be, both are same, that will be E just xi only, xi is xi, and xi minus mu I, xi minus mu I, j and I are same now. So, xi minus mu I whole square, which is the variance sigma xi square, variance of xi, which is greater than equal to 0. Variance cannot be negative, because this is square and then you are averaging. So, this cannot be negative. Okay. So, I stop here. We will discuss properties of correlation matrix and covariance matrices in the next class. Thank you very much.